Hey guys, IBM is here, and I think this is going to be part 10. Part 10 of magnetic fields and electromagnetic induction. I think in part 9 we stopped on this question here, so we are going to part 10. We are starting with question 23. State what is meant by a field of force. A field of force. Now, a field of force can apply to electric fields, it can apply to magnetic fields, it can apply to gravitational fields. So it's just a region of space where an object, where a particle experiences a force. So this is a region of space, where an object, or a particle experiences a force. So that is a region of space where a particle experiences a force. Explain the use of a uniform magnetic field and a uniform electric field for the selection of the velocity of charged particles. You may draw a diagram. Many times when they ask you to draw a diagram, when they say you may draw a diagram, it's because the diagram makes explanation easy without putting in a lot of effort to explain anything. So I will represent a uniform electric field with parallel plates, as we saw in electric fields. So let me draw parallel plates here. Okay, so let's say we have these are parallel plates, and I will say let one of the plates be positive. Let's say this is positive. Let's say this is negative. So the particle we are going to consider entering this is going to be a positively charged particle. You could consider any other particle entering the field, but I'm going to assume that the particle entering here is a positively charged particle. So we are going to consider a positively charged particle entering the field. It is a positively charged particle entering the field with a velocity call it v. So this particle, because it is positively charged, it is going to experience an electric force. Of course, the electric force when a positively charged particle is in the same direction as the electric field. So the electric force is going to be vertically downwards. So I'll call this one force due to the electric field. Then I'm going to introduce a magnetic field in here. So to show that there is a magnetic field here, I'll put in these circles, and I'm going to put the magnetic field is going to be perpendicular. It must be perpendicular to the electric field. So I'm going to put this into the page for simplicity. I've put it into the page because I know that if the particle is entering in this direction here, and the field is into the page, that is the first finger pointing into the page by Fleming's left-hand rule, the thumb is going to be pointing upwards. So the magnetic force is going to be upwards. Force due to the magnetic field, I can call it Fm. So if these two forces are equal, then the particle should go through without being deviated. It would continue in this direction here. So this is magnetic field. Magnetic field into the page. And the plates are showing a uniform field. So if the two forces F due to the magnetic field equals to the force, the electric field, then it means that B QV is going to be equal to Q times the electric field strength, which would mean that the speed V is going to be equal to E over B. For a particle to go through, its speed, the speed with which it enters the field must be equal to E over B. If it is greater or less, it will undergo deflection. But if it is equal to E over B, then the particle will just pass through without being deviated. So we can now put this in explanation. So the electric field and the magnetic fields are perpendicular to each other and to the velocity of the particle. So the electric and magnetic fields are perpendicular to each other and they're perpendicular to each other and to the velocity and to the velocity of the particle. For example, the electric field is downwards, the magnetic field is into the page, so they are perpendicular. The velocity of the particle is towards the right, so they are perpendicular. They are perpendicular to each other and to the direction, to the velocity of the particle. So the fields are such that the electric and magnetic forces on the particle act in opposite directions. The fields are such that the electric and magnetic the electric and magnetic forces on the particle act in opposite directions. So now that the electric and magnetic fields act in opposite directions, so we have to adjust the fields so that the electric force is equal to the magnetic force. The fields are adjusted. The fields are adjusted so that the forces are equal and the particles with speed. Particles with the speed v equals to E over B are selected. Particles with the speed v equal to E over B are selected, where E is the electric field strength and B is the magnetic field strength. So if I draw the diagram, I may not need to write the first and the second statements because the diagram I've drawn here is showing that the electric field is downwards, the magnetic field is into the page. And then the velocity is to the right. So this means they are perpendicular to each other. The fields are such that the electric force and the magnetic force on the particle act in opposite directions. So by selecting the patterns I've selected, the electric force is downwards, the magnetic force is upwards, so the forces are in opposite directions. What remains is just to tell the examiner that the fields are adjusted so that the forces are equal, and the particles with the speed v equals to e over b are selected, where e is the electric field strength and b is the magnetic field strength. So if I draw the diagram, it's only important that I write the last statement there to get full credit. A beam of charged particles enters a region of uniform magnetic field, magnetic and electric fields as shown, as illustrated here. This is a region of a uniform magnetic and electric field. The direction of the magnetic field is into the plane of the paper. Okay, so the field is into the plane of the paper. I'll use a cross to mean into the plane of the paper. The velocity of the charged particle is normal to the magnetic field as the particles enter the field. So since the velocity is perpendicular to the magnetic field, it means the particle experiences a force in accordance to Fleming's left-hand rule. The particle in the beam has a mass m, charge q, velocity v. The particle passes undeviated through the region of the two fields. Of course, when the particle passes undeviated, it's only because the electric force is equal to magnetic force. On the figure, sketch the path of the particle that has mass m, charge positive 2q, velocity v. Label this q. And the second particle, mass m, charge q, velocity v, label this capital V. So, since the magnetic field is into the page by Fleming's left-hand rule, at the point where the particle just enters the field, the magnetic force is going to be upwards since the particles are positive. So the magnetic force is going to be upwards since the particles are positive using Fleming's left-hand rule. Second finger, the direction of the particle. First finger into the plane of the paper, that is into the field, into the page. The thumb points upwards, so the magnetic force is upwards. So the force is upwards, direction of the particle, velocity, then the direction of the magnetic field. So the magnetic force is upwards, which therefore means the electric force is downwards. Okay, so the path, remember the path depends on V equals to E over B. It is not depending on the charge, it is not depending on the speed. So the path depends on E over B. So for the first particle, for Roman 1, the velocity is unchanged, then the particle is also undeviated. The particle is going to be undeviated because the velocity remains the same. The velocity was not changed, and we know that V equals to E over B. So the velocity is unchanged, so the particle is going to just continue without being deviated. So Q is going to be here. So this is going to be Q, because the velocity V equals E over B, and the velocity has not been changed, so V has remained the same, even though the charge is twice Q. Then for the first one, the mass is M. For the second one, the mass is the same, and the charge is the same, but the velocity is slightly larger than V. Remember, V is E over B. So if if the velocity is greater than V, in other words, the new velocity V prime, I'll quote V prime, is greater than V, which means it is greater than E over B. What does that mean? It means that B Q V prime, that is the magnetic force, is greater than Q times E. So this means the magnetic force is greater than the electric force. So if the velocity is greater than E over B, it means the magnetic force is greater than the electric force. So the resultant is going to be vertically upwards. The resultant force is vertically upwards. Therefore, the particle will follow. Because the magnetic force is constant, then the particle will be deviated upwards, so it will follow this path. The particle will follow that path, but remember, when it emerges, it just continues in that straight line. When it emerges, I'll just put a tangent here. Okay, so I'm going to label this V. capital V. If the speed was slightly less than V, it would mean that the electric force is greater than the magnetic force. And since the electric force is downwards, then it would mean the deflection would be downwards. So that is the solution to that question. An electron having charge minus q mass m is accelerated from rest in a vacuum through a potential difference V. The electron then enters a region of uniform magnetic field of flux density B as shown in the figure here. The direction of the uniform magnetic field is into the plane of the paper. The velocity of the electron as it enters the magnetic field is normal to the magnetic field. So if the velocity is perpendicular to the magnetic field, then the particle is experiencing a force as predicted by Fleming's left-hand rule. The radius of the circular path of the electron in the magnetic field is r. Explain why the path of the electron in the magnetic field is the arc of a circle. So, because the magnetic force is constant and always perpendicular to the direction of the particle, then the magnetic force does not change the speed. It simply changes direction. Therefore, it causes a centripetal acceleration, which is actually causing a centripetal force. The speed does not change, so there is no work done. Therefore, the magnetic force does not do work, but simply provides a centripetal force. Because this is 3 marks, so I will simply say the magnetic force is constant and always perpendicular to the velocity. And always perpendicular to the velocity or perpendicular to the direction of motion. So the speed is constant or remains constant. Kinetic energy is constant. Oh, I can say there is no work done. There is no work done on the electron. There will be no work done on the electron. So the magnetic force just provides centripetal force. The magnetic force just provides centripetal force, which just provides centripetal acceleration. So causing the body to move in a circular path. Show that the magnitude P of the momentum of the electron as it enters the magnetic field is given by that expression. So before it enters the magnetic field, it is accelerated through a potential difference, which was V. So the loss when it enters the magnetic field, the loss in electric potential energy should be equal to the gain, or before it enters the magnetic field, the loss in electric potential energy is going to be equal to the gain in the kinetic energy. So the loss in electric potential energy is equal to the gain in kinetic energy. That is before it enters the magnetic field. But electric potential energy is charge times accelerating PD. Kinetic energy is going to be a half times mass times the speed squared. So multiplying both sides by m, we have that this side I have m q v equals to m times a half m v squared. So on the right hand side I have m squared v squared being equal to twice m q v. And of course you and me know that m squared v squared is equal to momentum squared. So I'll say that momentum squared equals to twice m q times v, which when we find the square root, p is going to be the square root of twice m q times v. The potential difference V is 120 volts. The radius R of the circular arc is 7.4 centimeters. Determine the magnitude B of the magnetic flux density. So since we now notice that the magnetic force BQV provides the centripetal force, that is mv squared over R. So it means that BQR is equal to m times V. And of course, you and me know that mv is momentum. So it means that BQR is also the same as momentum. Dear pain, it is the last video. So this is the same as momentum, which we have seen as square root of 2mqv. So this is square root of 2mq times the accelerating PD. So it means I'm going to just equate this to this, and I make B the subject. So B is going to be the square root of twice mqv divided by q times r, which is going to be square root of twice. The mass is 9.11 times 10 to the power of minus 31 for the electron. Then times the charge, 1.6 times 10 to the power of minus 19 for the electron. The accelerating PD was 120. Then divide by the charge, which is 1.6 times 10 to the power of minus 19 coulombs. The radius is 7.4 times 10 to the power of minus 2. So pressing my calculator here, I have the 2 times 9.11 exponent minus 31, then times 1.6 exponent minus 19, then times 120, divide by, okay, I have to first find the square root of the answer, then divide by 1.6 exponent minus 19, divide by 7.4 exponent minus 2. So that is 4.995 times 10 to the power of minus 4 Teslas, which is actually 5.0 times 10 to the power of minus 4 Teslas. The potential difference V in C is increased. The magnetic flux density B remains unchanged. So V is increased, B remains unchanged. By reference to the momentum of the electron, explain the effect of this increase on the radius r of the path of the electron in the magnetic field. So we have seen that momentum equals to BQR. V is increased, and we see that the momentum is independent of V. So that means the radius is going to remain the magnetic flux density B remains unchanged. The potential difference V is increased. By reference to the momentum of the electron, explain the effect of this increase on the radius r of the path of the electron. So momentum is equal to pqr, and momentum is also equal to the square root of twice mq times v. So when v is increased, momentum is increased. When momentum is increased, then r is increased, because root of v is directly proportional to p, and p is directly proportional to r. So I'll say from momentum equals to square root of twice m qv, increase the v, increase the value of v implies a greater momentum, implies a greater momentum. And from momentum equals to bqr, from momentum equals to bqr, a greater momentum implies that r increased. So the radius increased. Okay. A Hall probe is placed near to one end of a current carrying solenoid, as shown in the figure here. The probe is rotated about the axis xy, so it's rotated just about the axis xy, and is then held in a position so that the Hall voltage is maximum. It's held in a position so that the Hall voltage is maximum. Explain why a Hall probe is made from a thin slice material. They didn't mention the material, so it could be semiconductor or it could be a conductor, but it is thin, so it is the thickness is the one which is very important here. So VH equals to BI over NTQ. So we notice that VH is inversely proportional to thickness. So we should say a Hall voltage depends on the thickness of the slice. Hall voltage depends on the thickness of the slice. Hall voltage depends on the thickness of the slice. The thinner the slice, the larger the Hall voltage. The thinner the slice, the larger the Hall voltage. So VH is inversely proportional to T. So the smaller the value of T, the larger the Hall voltage. And I mentioned that a large quantity, when measured, has a smaller percentage uncertainty. So making the slice thinner means that the value of VH is larger, and measuring VH as a larger value would give a smaller percentage uncertainty. In order for consistent measurements of magnetic flux density to be made, the current in the probe must be constant. I've already mentioned that VH is equal to BI over NTQ. If I is not constant, then it means VH is going to be affected. So we say Hall voltage also depends on the current in the slice. Hall voltage also depends on the current in the slice. In bracket, VH is directly proportional to the current. So if the current is not constant, it means the Hall voltage will not be constant. Keeping the current constant, then the Hall voltage is not going to be affected. So if the current is not kept constant, then the whole voltage is affected. So if we don't want the whole voltage to be affected, then we should ensure that the current remains constant. The probe is now rotated through an angle of 360 degrees about the axis. Remember, it started from maximum. It was first held at a position where the whole voltage is maximum. So the graph at t equals to 0. Sorry, when the angle, we are starting from maximum. At angle theta equals to 0, the whole voltage VH has the maximum value Vmax. So at theta equals to 0, the whole voltage is Vmax. On the figure, sketch the variation with the angle theta of the whole voltage for one complete revolution. So one complete revolution means we are going to come back to where we started it from. So that means the final value should also be maximum. The final value should also be maximum 1, 2, 3, 4, 5. Okay. But of course, we know that since theta equals to 0, for theta equals to 0, Vmax of Vh is maximum. Vh equals to V max. So that means Vh in general is going to be B cos of theta times the current. Then this is divided by N T Q. Because if theta is 0 and Vh is not 0, then the component is B. It is going to be B cos theta. The component of the magnetic field perpendicular to the current is B cos theta. Therefore, you can check for theta equals to 90. You and me know that cos of 90 is 0, so Vh is going to be 0. So this goes to 0. Then you can check for theta equals to 180. Cos of 180 is negative 1, so Vh is going to be negative Vmax. So at 180 we have negative Vmax. I'll just subtract 1, 2, 3, 4, 5. Okay, then we can check for theta equals to 270 degrees. Cos of 270 degrees is actually 0. So Vh goes to 0. Then for theta equals to 360 degrees, cos of 360 degrees is 1. So it means Vh is again going to be Vmax positive. So the graph is going to take this shape. Okay, so you can draw a better graph, but I think it takes that shape. And I think that should mark the end of part 10. Until next time, bye bye.